Hi folks, today we're going to take a look at a process called completing the square. And what completing the square allows us to do is to take a function in standard form, ax squared plus bx plus c, and to rewrite it in vertex form. So y equals a times x minus h all squared plus k. And of course, you know that vertex form is useful for trying to find the maximum or minimum of the function. So we're going to start off with the easier example, which is when a is equal to 1. Okay, so what we have to do is write then y equals x squared plus bx plus c in terms of x minus h squared plus k. So in order to do this, we're actually going to go backwards because we do know how to go from vertex form to standard form, and we'll do that and see if it offers any help or any hints on how to go the other way. So I'm going to start off with x minus h squared plus k. And if I did want to write that in standard form, I know that I just have to expand this perfect square. So we'll do that, x minus h times x minus h. And we expand that out, x times x, x squared. Negative hx minus another hx gives me minus 2hx, and then negative h times negative h is plus h squared. And don't forget that we still have the plus k here, plus k here. Okay, but what I want to focus in on is that perfect square. And when we expanded x minus h all squared, we got this trinomial, x squared minus 2hx plus h squared. So what our goal is going to be is, when we're working with standard form, can we somehow manipulate this expression so as to achieve this specific trinomial of the form x squared minus 2hx plus h squared? Because we know that this is going to be equal to the perfect square we're looking for, that's x minus h all squared. Now we know that sometimes the vertex form is actually given as x plus h all squared plus k. So let's just make sure that it's not too different, and I think we'll see that it won't be. So if we expand this out, x plus h times x plus h, okay, and then plus k, of course, and x times x, x squared, hx plus another hx, so plus 2hx plus h squared, and then plus k. And here we see that the perfect square x plus h squared is equal to the trinomial of the form x squared plus 2hx plus h squared. So we need to achieve one of these two trinomials, which will then allow us to factor it perfectly as the perfect square which we see in vertex form. Okay, so let's take a look at an example here. So I'm going to take the example y equals x squared minus 10x plus 3. Okay. So first of all, we notice that this is, I think we can see pretty clearly that this is not factorable. So the idea of using the zeros or the x-intercepts to help find the vertex won't work out. We could use partial factoring, just working with the first two terms, but as we remember, that's a pretty long and involved process, so I'd like to try to avoid that. So we're going to see what we can do with this idea of creating a perfect square. So I notice I have minus 10x, so I'm going to be working with this example here. So I already have the x squared. Good start. Now I know that the coefficient of x needs to be written as 2 times some number. So I look here and I say, well, can I write 10 as 2 times some number? I realize, yes, I can write that as 2 times 5. Okay. What this means is that the 5 now becomes our h value. Okay, now this is where we have to be a little clever, because when we look at our general form of the trinomial, we see that I now have my 2 times h, but I also need a plus h squared. So in this case here, plus 5 squared. And this is an old trick that we're going to use, is if we need a plus 5 squared, well, we're just going to put it in. We need it, so let's put it in. Problem is that now we've actually changed the value of the expression, because we've added something that wasn't there before. And the way we deal with this is by also subtracting that number from the expression. So when you look at it, all I've done here is I've added 25, but I've also subtracted 25, thereby not really changing the value of the whole expression. And then, of course, let's not forget that we have the plus 3. Now, why this is useful is because if I look at the first three terms, it's exactly the format I need to get my perfect square. I have x squared, minus 2 times 5x, 2 times hx, so h is equal to 5, and we've got the plus h squared plus 5 squared. So, judging by this equality up here, I know that the first three terms of this expression just factor perfectly as x minus h, which in this case is 5 squared, and then all I have left to do is to simplify what remains. So minus 25 plus 3, and so I have x minus 5 all squared, negative 25 plus 3 is minus 22, and I've accomplished what I set out to accomplish, which was to take this quadratic function in standard form and to rewrite it in vertex form. So here now I can read off the vertex just by looking at the equation, 5, negative 22. Okay? Now, when we look back at that first step, we see that it was made easier by the fact that I had an even number. It was very easy to write this as 2 times some other number. Okay, well, let's look at an example where it's not an even number, and we'll see that things don't really change much. So let's take a look at the function y equals x squared plus, we'll use an addition here, 5x minus 1. Okay. So again, notice how we don't even bother with that c value. We just leave it apart and we deal with it only at the very end. So I need to write this in the form that we need. So let's remember I need x squared. And I need to write this as 2hx. So 2 times what number is equal to 5? Well, 5 divided by 2 is 2.5. So even if I don't get a perfect integer, I don't worry about that. I don't expect to always get a perfect integer when I find the maximum and minimum. But I've achieved what I needed to achieve, rewriting it as 2 times hx. So that means here the h value is equal to 2.5. Okay, then I look back, I know I need my plus h squared, so I need plus 2.5 squared. Now, as I get better at this, I'm going to try to actually do this in less steps. So right away, I'm going to write out h squared, which is 2.5 times 2.5 is 6.25. So this is my h squared. And then, of course, since I've added something new, I also have to subtract it. And then don't forget that I've got my minus 1. So again, when I look, the first three terms give me exactly the form I need to get my perfect square. So that means that these first three terms factor perfectly to x plus h, which in this case here is 2.5, all squared. And then all I have to do is simplify these two numbers here. So negative 6.25 minus 1 is minus 7.25. And now we see that in 2 steps, I've managed to get the maximum and where the maximum occurs, so the h and k values of the vertex. If we think back to what we did earlier, we had to factor, find the zeros, take the average, and then from there stick that back into the equation to get our maximum or minimum. Quite a few steps. Here, in 2 steps, with just a bit of clever algebra, I'm able to get the maximum of the function, or in this case here, the minimum of the function, and where it occurs. In other words, the vertex. Okay, so in the next video, we'll take a look at how to deal with quadratic functions where a is not equal to 1.